Okay, we're going to try to get an understanding of how similarity and side ratios in right triangles are properties that are special to those right triangles, and it's going to help lead us to definitions of trigonometry and how ratios work for determining acute angles in triangles. So first of all, what we're looking at is this 90-degree triangle, and I have all the angles marked here, 90 degrees, 30 degrees, and 60 degrees here, and I have two sides marked. So first of all, what we're going to do is we're going to find this missing side, and we're going to do that in the traditional way of using the Pythagorean theorem. One thing to keep in mind is the c value in the Pythagorean theorem is always the hypotenuse, which is opposite of the 90-degree angle. So we're looking at L squared plus 1 squared is equal to 2 squared. So this is the first leg, the A side, this is the B side, and then this is the hypotenuse. So we want to solve for this L value. So first of all, we're going to take everything to the second power. According to order of operations, we do the parentheses first and then exponents. We don't have parentheses, so we're doing exponents. So L squared plus 1 equals 4. And then we're going to subtract 1 from each side. We're going to have L squared equals 3. And then take the square root of each side. So the missing side is the square root of 3. And we're going to leave it like this. We're not going to try to get a calculator value with a decimal. So this missing side we can fill in as square root of 3. Now I'm going to create another triangle with the same angles but different side lengths. So according to the definition of similar polygons, this is going to be a similar triangle, and we're going to look at side lengths in it, and then we're going to look at the two triangles together and compare some ratios. Alright, the next triangle we're looking at has 90, 30, and 60 also, and what I've done is I've just made something that has side lengths cut in half. So 2 divided by 2 is 1, 1 divided by 2 is a half, and square root of 3 divided by 2 is square root of 3/4. So how does this similar triangle compare to this one? Well, according to similar triangles, the sides should be in ratio, and we've already established that. Going from this triangle to this triangle, I'd multiply each of these sides by half, or going from this triangle to this triangle, I'm going to multiply by the reciprocal of that, 2, and multiply each of these sides by 2 to get this triangle. So we have that similarity. We have the congruent angles, those are given. So now what are we going to look at? We're going to look at ratios. I want to look at the ratio of the hypotenuse to this height. And I'm going to make a note of that out to the side. So the ratio is going to be 2 over the square root of 3. Now I want to do the same thing here. I want to look at the ratio of the hypotenuse to this height, and I get 1 over the square root of 3/4. So what does that tell me? Well, I'm going to bring in the calculator on this one so we can see an exploration about what the calculator is going to tell us about these two ratios. So everything's going to be converted to a decimal, but hopefully that decimal is going to help us understand what is really going on with these ratios. All right, looking at the calculator, when I type these two ratios in, we see that 2 divided by the square root of 3 is approximately 1.547. When I type this into the calculator, I get the same decimal number. So even though these are two different triangles, and they have two different side measures, we are seeing that when we divide the hypotenuse by this leg on each of these, we get the same number. And that is part of the specialness of special right triangles with trigonometry, is that these ratios between different sized triangles end up coming out with the same value. And this is the typical type of value that you get when you do trig on a calculator. You get some decimal number, and it just continues on as far as your calculator is willing to produce numbers. So this is an important concept that we need to learn, is that special right triangles, and that's what we call these, have these consistent ratios in them. So if we look at this side that's opposite the 30 degrees, we see it's a half. The side opposite of this 30 degrees is 1. And then the hypotenuse is 2 over here. The hypotenuse is 1 over here. We looked at the hypotenuse and this side on both these triangles, but now what about this opposite side and the hypotenuse? Do they also have a special property? Well, we can look at that again, a new ratio. So the opposite side over the hypotenuse is a half. Opposite side over 1 is a half, which is equal to a half. So this one readily, we can see without a calculator that they're going to be the same thing. So we see that these ratios hold in it. There wasn't anything special about this side over this side. So now let's take a look at this side, the opposite side, and this adjacent side to this 30-degree angle, and the opposite side over the adjacent side. This one we'll probably want to bring the calculator back in on. I'm going to write this opposite side over the adjacent side, and I get this 1 over the square root of 3 here, and then I'm going to have 1/2 over the square root of 3/4 here. And so we'll bring the calculator back in on this one. As we look at these ratios again, we see that they are the same decimal numbers. And so it doesn't matter how we go around the triangle, we get these consistent ratios, even though the triangles are physically different sizes. The only thing that's staying the same between this triangle and this triangle are the angles. And then we now learn that these ratios here and here are also remaining the same. So there are a couple of things that are invariant in these two triangles. And this is going to hold for any triangle that we look at that has a 30, 60, 90 structure to it. So this becomes what we call the 30, 60, 90 special right triangle theorem. All right, this is the theorem that we're looking at. Given a triangle that has 30, 60, 90 angles, we're going to have sides that have this consistent proportionality. If you know the base side, that's some value n, where n is a real number. Then the hypotenuse is going to be 2 times that number, and the height is going to be n, this value, times the square root of 3. And this will hold for all triangles that have the 30, 60, 90 angles to them. So this is a new theorem for us. And we're going to get another one that's very similar to this also, called the 45, 45, 90 special right triangle theorem. That's also going to be one that we're going to want to have. And it has these special kind of proportions to the sides as well. Cheerful calculations.